Hi everyone, this is the review video for Unit 4 electromagnets. So the idea behind electromagnets is that electricity and magnetism are very closely related. And when we use the concepts of electricity and magnetism together, we can really make some big advancements in technology that uses electromagnetism. So that's what we're going to be looking at in this unit. Now, before we can look at electromagnets as a combination, we need to look at these two things, electricity and magnetism, separately. So with electricity, the essential idea is circuits, okay? Circuits are basically loops of wire that allow electrons to flow, okay? Loops of wire connected to allow electrons to flow. Now, when a circuit is closed, electrons are free to flow through the loop, right? So when closed, electrons flow. And that's what we use switches for. So when the switch is off, that means your circuit is open and electrons cannot flow. And so that's why your electric device doesn't work. When you turn the switch on, you close the loop or the circuit and electrons are allowed to flow. Circuits transfer electrical energy. And they allow electrons to flow towards a positive charge. So electricity is, all it is moving electrons. When electrons are allowed to move from one location to the next, that's what electricity is. Okay, so if I draw a simple circuit for you here, I have a battery, right, and it has two leads, plus and minus leads, and I connect a wire from the battery to a switch, right, so this is what we call a knife switch, right, if I close it, I can close the circuit, and then I connect another wire from the knife switch to, let's say, a light bulb, right? I want to turn the light bulb on. And then I'll have to connect another wire from the light bulb back to the positive end of the battery. So once I close this switch, once I push it down and make a connection, then electrons, I'll just use E for electrons, are allowed to flow through this loop of wire. They go through the bulb, light up the bulb, and continue to move towards the positive side of the battery. So that's a circuit. Okay. Now, associated with circuits are three very important ideas that I'll list right here. The one is current. Current is basically the rate of electron flow. In other words, how fast are the electrons moving? How fast? Voltage. Voltage describes the potential difference, or how badly do they want to move. The potential difference that drives the flow. And resistance, current, voltage, and resistance. Resistance is anything that uses up electricity, or sometimes we refer to it as the opposition to the flow of electrons. Okay, opposition to the flow of electrons. These three ideas, current, voltage, and resistance, are all related to each other through something we call Ohm's law. Ohm's law has an equation, V equals IR. Okay? So the voltage is equal to the current of a circuit times the resistance in that circuit. So for example, if I have a voltage of 12 and I have a current of, let's say, 0.5, I can use this equation to calculate the resistance. In this example, my resistance would be 24 ohms. Okay, so that describes the opposition to electricity or electron flow. Now, related to this idea of current, voltage, and resistance is electrical power. Electrical power is defined as the rate at which energy is transferred. So how fast is energy transferred? The equation for power is going to be current times the voltage. Current times the voltage. You can also describe power as the energy per unit time, like how many joules per second. All right. The power rating of a light bulb is something you're familiar with, like a 100-watt light bulb uses 100 joules of energy per second. Okay, so that's electricity. Now, magnetism is similar in a lot of ways to electricity, but also different in some ways. So we know that in magnetism, like poles repel. Like if I put two north ends together of a magnet, they will repel each other, and opposite poles attract. So what we can do to describe the strength of magnets is we can use what's called magnetic fields. Magnetic fields are invisible, okay? They cannot be seen. But we can use iron filings or something that's magnetic to sort of look at the magnetic field that is otherwise invisible. Okay, so if you use iron filings and you pour it between two magnets, you will see a pattern that the iron filings take. And what you'll notice is that if you have two magnets that have their same poles facing each other, opposite poles facing each other, what you'll notice in between is that there is a very strong attraction between, there will be lots of iron filings in this area where the attraction is occurring. Okay? And you'll see iron filings move all around the magnet, but you're going to see more iron filings right in the middle where the attraction is happening. If you have two magnets that are facing north end to north end, like I'm drawing here, what you'll see is the iron filings or iron shavings will, of course they're not going to be arrows, I'm just drawing arrows to kind of show you what's happening, but they're going to want to move away from that area because of that great force of repulsion. And what you'll notice is that there will be no magnetic field in the middle, okay? Because those two ends or poles are repelling each other. Now, where does magnetism come from to begin with? Where does magnetism come from? So let's talk about that. In some metals, there are areas of electrons that all spin in the same direction. These are called domains. Okay? So, in a non-metallic substance, in a non-metallic sample, so here are the domains. These are just the areas of similar electron spin. Areas of similar electron spin, but those spins are in random directions. Okay? So they are not all spinning in the same direction. So this is not magnetized. If you bring a magnet close to this substance, right, so if I bring a magnet close, what will happen is I can get, and this only happens in some substances, right? So like you can't magnetize like a wooden table, but some metals can be magnetized, because what will happen is if you bring a magnet close, you will get all these domains to line up and go in the same direction. And when they do that, you basically get a north and south pole here. You get a north and south pole, which magnetizes the substance. Okay, so this is magnetized. So the way to magnetize something is to align the domains of the electrons inside that material. All right, so this brings us to the idea of electromagnetism. So we know that magnetism is closely related to electricity. Closely related to electricity. Because of the alignment of the electrons. Okay, when we talk about electrons, we're referring to electricity. When we're talking about the electrons all lined up in the same direction, all the domains facing the same direction, we're talking about magnetism. Okay? Now, a magnetic field can form around a wire that has current or electrons moving through it. Okay? So, this is called an induced magnetic field. It's just a fancy word that you're creating a magnetic field by running electricity through a wire. So what this means is, we'll write the definition first. A magnetic field forms around a current carrying wire. Okay, so if I have a wire here, here's my wire, and I send current through this wire, right? So I'm going to send current, and I'm going to label it I because I stands for current. And I send current up the wire. What I will notice is that around this wire, I will get a small magnetic field. Okay? I can create this small magnetic field simply by putting electrons through a wire. Now, the direction of the magnetic field is always perpendicular to the current. Perpendicular, that means 90 degrees to the current. And the direction depends on the direction of the current, okay? The direction of the magnetic field depends on the direction of the current. Depends on the direction of the current. So in other words, if the current was going down the wire, the magnetic field would be going in the other direction. Okay, so I'll draw another example here. If I had a wire and my current was going this way, then the magnetic field would be spinning, in the other direction. Okay? All right. You can make an electromagnet if you take a nail and you wrap wire around the nail and then connect that to a battery. You've basically made an electromagnet. So wrapping wire, loops of wire, have a special name. So we'll say loops of wire can create strong magnetic fields inside of them. So in other words, if I take this wire and I make a loop out of it, like this, what I will notice is that the magnetic field inside the loop of wire will be very, very strong. Right? This loop of wire has a special name. It's called a solenoid. And a solenoid can act as a very strong magnet because there's so much wire wrapped around that it creates a huge magnetic field. All right, now the opposite of this idea is also true. Just like you can make a magnetic field by running current in a wire, you can also make current run in a wire by changing a magnetic field. Okay, so that is called an induced electrical field. We'll call it induced electricity. So this is basically when a magnet or magnetic field moves near a wire, current will run through the wire. You can literally make the electrons in the wire move by just moving a magnet around a wire. Okay? So if I have a wire, I'll do the best to draw a picture. If I have a wire and I have a magnet and I spin this magnet around near this wire, I can get electrons to move through the wire just by changing the magnetic field near the wire. So that's called induced electricity or induced electric field. And we can generate electricity this way. So electric generators use energy like steam or wind energy from a windmill, use energy to spin magnets near a coil of wire. Near coils of wire. And that's how we generate electricity at our power plants. So essentially, at the power plant, you have, just these giant coils of wire just kind of sitting there. And then outside of that, you have something spinning around it that has magnets in it. So, if, for example, in a windmill, that centerpiece of the windmill that the blades are attached to, I can't draw, you know that. This centerpiece has magnets in it. And that magnet is spinning around a coil of wire, which then causes electricity to be generated in the wires. And that electricity is captured, stored, and sent to your home so that you can turn on your lights and charge your cell phone and watch TV and use your computer and all that good stuff. Okay, so once again, you can induce a magnetic field by running current in a wire, and you can induce an electric field by moving a magnet near a wire, and that's how most of our electricity in this country is generated. It's generated by moving a magnet near large coils of wire and then capturing the energy the electrical energy that's generated there. Okay, I hope this helps. If you have any questions, please stop by office hours.